Hello. So we are starting with polymers again, and we are going to discuss today several different polymeric examples. In these examples, first of all, we are going to discuss two, that is LDPE and HDPE. Both are nothing but different types of polythene. But this polythene is divided into two, that is a low density polyethylene and a high density polyethylene. Generally, polythenes are linear or slightly branched long chain molecules. So, whenever polythene is asked, you must go for it as a linear polymer with few branches, if at all required. But there is an important point that comes over here if you can go through your book. These are capable of repeatedly softening on heating and hardening on cooling and are thus thermoplastic polymers. So over here I am just going to discuss another point, that is thermoplastic polymer and thermosetting plastic polymer. Whenever I use the word thermoplastic polymer, these polymers change their property, that is they get softened on heating and again gets hardened on cooling. But such a property is not observed in thermosetting plastic. So as this property is observed over here, these polythenes are thermoplastic polymers. Now, what is the difference when it comes between LDPE and HDPE? But before going into the difference, let us just study it, how it is. So, you have a simple ethene molecule. When several ethene molecules combine with each other, the pi bond breaks. As the pi bond will break in both these cases, if you can imagine, it will liberate each electron on one carbon, as it is a homolysis, equal breaking. So these two electrons will combine and form a new bond. Similarly, there will be one more molecule on this side, so a bond over here and a bond over here. So you can just imagine a long chain on both the sides. And I can make you imagine if I write that I am taking n moles of ethene, and when we undergo the process of polymerization, we can get a long chain of polymer, and this long chain of polymer is called polythene. Although this is a very simple reaction where n moles of ethene helps you get converted into n moles of polythene, many more important points are to be remembered over here, which includes in a two different way. And when we go for that, we are now going to describe a bit of LDPE and HDPE. Low density polythene is obtained by the polymerization of ethene under a high pressure of 1000 to 2000 atmospheric pressure and 350 Kelvin to 570 Kelvin. So the temperature and pressure are too high, and in presence of traces of dioxygen and peroxide initiator or a catalyst. The low density polymer is obtained through a free radical polymerization. So the method is also given here as free radical polymerization, and it has few branches. But for us the important point is in LDPE, the temperature, the pressure. Moving a step ahead in the same system where we are working, and if we shift from LDPE to HDPE, just observe what happens. When we shift from LDPE to HDPE, then the temperature and the pressure are reduced. Rather than using a high temperature up to 570 Kelvin, the reaction just proceeds smoothly between 333 Kelvin to 343 Kelvin. And the pressure is brought down just to 6 to 7 atmosphere. And now comes the question, how is it possible? And when we go towards its possibility, we can see that Zn catalyst plays a key role. So now comes the question, what is this Zn catalyst? It is the Ziegler-Natta catalyst. Now, what is this Ziegler-Natta catalyst? Ziegler-Natta catalyst is triethyl aluminum plus titanium trichloride or titanium tetrachloride. This combination is added into the reaction vessel along with your ethene polymer, and it will result into a product that is HDPE, high density polyethylene. So this is how you can obtain both required products, that is LDPE and HDPE, with a very basic and a genuine difference of just a catalyst, which is a Ziegler-Natta catalyst. So these are the first two reactions. Moving forward in the same, we have a very important product obtained over here, and that is popularly known as Teflon. You might have heard of this Teflon as it is used in coating of these non-stick cookwares. This Teflon is also known as polytetrafluoroethene. Polytetrafluoroethene, popularly known as Teflon. This polytetrafluoroethene, popularly known as Teflon, is prepared by a very simple method where the hydrogen of ethene are replaced by fluorine. It's a carbon-carbon double bond with 4 fluorine atoms. When it undergoes a reaction in presence of a catalyst at a high pressure, the pi bond breaks and a simple long chain of this coating material is obtained, which is called Teflon. So this is how Teflon is prepared. It is manufactured by heating tetrafluoroethene with a free radical polymerization method where persulfate catalyst is used at high pressures. So let it be LDPE, let it be HDPE, let it be Teflon. All three have undergone a very simple free radical polymerization reaction. The major difference in all the three are the catalyst. In the first, if you look into very carefully, the catalyst was peroxide either as an initiator or as a catalyst. Don't judge initiator and catalyst to be same always. A material or a chemical that helps in initiating the reaction is called initiator, and sometimes this initiator itself plays the role of a catalyst. And the same thing happens when it is LDP. This peroxide plays a dual mutual role of a catalyst as well as an initiator for LDPE. But when you go for HDPE, you shift to Ziegler-Natta catalyst, and when you go for Teflon, you are coming towards the third one, that is the persulfate catalyst. It is chemically inert and resistant to attack by corrosive reagents. It is used in making oil seals, gaskets, and also used for non-stick surface coated utensils. So we are done with this Teflon. And again, just for your remembrance, do not forget to comprehend what you are learning. Comprehending the things is very important. For example, as I am done with HDP, LDP, and Teflon, I must make few notes, comprehends in my book that as it was LDP, it was free radical. Here also it was free radical. Here also it was free radical. All three, pi bond was breaking and sigma bond was making. So if you remember, if only pi bond breaks, it is addition reaction, and were two different molecules combining? No, two same molecules are combining. It is homo addition reaction. But now comes the difference. LDPE had peroxide as a catalyst, Teflon had persulfate as a catalyst, and very popular Ziegler-Natta catalyst in HDPE. So this is comprehending. This is comprehending. This has to be done. This is very important. Moving towards the fourth one, popularly known as PAN, Poly Acrylonitrile. This PAN has multiple names as that users suggest. Polyacrylonitrile is also popularly known as Orlon. Remember it very well. It is popularly known as Orlon. It is also addition reaction. In this addition reaction, you have this molecule. This is cyano. This is ethene. So you can write it as acrylonitrile as it is given in your book. People also write it as vinyl cyanide. You cannot refuse it. People write it as vinyl cyanide because it's a cyanide group and it's a vinyl substituent. And third, in the form of an IUPAC, 1, 2, 3, prop 2 in 1 nitrile. So all three names are for this raw material acrylonitrile that is used for the preparation of PAN or ORLON. It undergoes again a polymerization reaction. When it undergoes a polymerization reaction in presence of a peroxide, you will get a very popular product. It is very simple. In all this product, if you look into this reactions very well, it is very easy. You are just breaking this pi bond and you are elongating the both side, and this is your polyacrylonitrile Orlon pan catalyst. Sorry, pan product, that is a polymer. So friends, this is how we did the LDP. We are doing with the HDP. We are doing with the Teflon, and a similar kind of task was performed for polyacrylonitrile. Now we are moving towards one more important section, and we were conducting addition homopolymers as of now that included LDP, HDP, Teflon, and at last polyacrylonitrile, popularly called Orlon. Now we are moving towards condensation reaction, and we are going towards co-condensation reactions. Co means two or more than two monomers combining together, and condensation, very well caught. Either water will come out, ammonia will come out, alcohol will come out, or acid will come out. These reactions are popularly known as condensation reactions. So when such is the task, we will mainly focus on two different classes of compounds that includes polyesters and polyamide. When we say polyester, our polymer should have that ester functional group, and we have a very popular example which is, and that is terylene, which is also known as dacron. And this terylene or dacron is a very popular example of the polyester family. So while preparing this dacron or terylene, we need to have two monomers respectively known as ethylene glycol, a very simple reactant which is also called as ethane 1,2-diol, combining with terphthallic acid. It is also a very simple molecule. If you can write it, it is benzene 1,4-dioic acid. Benzene 1,4-dioic acid or dicarboxylic acid. It should be benzene 1,4-dicarboxylic acid and not dioic acid. When these two combine, an OH from here and the H from here is eliminated. Similarly, an H from this side and a OH of another can be eliminated. OH from this side and then H from another can also be eliminated. So it is 1 2 1 2 1 2 pattern. Ethylene glycol terphthallic acid. Ethylene glycol terphthallic acid. So I write O followed by CH2CH2O, CO, a benzene ring, a CO. So this is one Dacron repeating unit. It keeps on repeating thousands of times, and that results into Caroline or Dacron. So this is how it works, friends. Polyester, Dacron. We have one more Dacron with us. Type of Dacron, not exactly Dacron, which is called glyptal. And in glyptal, the magic is this ethylene glycol is same. You will not change this ethylene glycol, but this benzene 1,4-dicarboxylic acid will change to benzene 1,2-dicarboxylic acid. And therefore, when you will write the product, it will look a little different. I'll show you how it looks. It looks like this. Okay, let me write it on the next page itself so it looks much clearer, because it is probably not given over here. You must know it very well. What I told you will change is one of the monomer will shift to benzene 1,2-dioic acid, and therefore it will look like this. This. And when you are writing this, spell it very well, it will look like glyptal. So these are the two popular polyesters available with us. And they are called condensation polymers because water was removed when the two molecules combined. So after moving from polyester, I would like to discuss polyamide with you. And when discussing polyamide with you, we will be doing this example nylon 66, a very popular example. Nylon 66 is nothing but a combination of hexamethylene diamine and adipic acid. And when I combine hexamethylene diamine with adipic acid, it is called nylon 66. Now, first of all, let us learn this 66. When I will write hexamethylene diamine, it will be CH2 6 times, NH2 and NH2. So this carbon is coming 6 times. And when I will write adipic acid, if you go calculating the carbon over here, 1 carbon, 2 carbon and 4 carbon, total 6 carbon. So as there are 6 carbon in each monomer, we will write it as nylon 66. H from here, OH from this side, H and OH consecutively will be removed. So you will end up writing something like this. So it is like this. So this is your nylon 66, 6, 4, 5 and 6. Nylon 66. Also over here it's a CONH group, so it's a polyamide. Here it was COO group, so it was a polyester. So this is how, friends, things work when you have few important polymers: LDP, HDP, Teflon, PAN, polyacrylonitrile, also known as Orlon, Terylene, a newer one, glyptal, and nylon 66. So we just discussed 7 different molecules. I wish you should go through this, and in the next video we'll come up with the remaining polymers very soon. Thank you.